In my previous presentation, I have shown you how to design a multiplexer. In this video, I will show you how to design demultiplexer. Demultiplexer performs the opposite function to that of a multiplexer. Multiplexer accepts data in different input channel and directs those data to a single output channel. But the demultiplexer accepts data in a single input channel and pass this data, or you can say distribute this data to different output channel. That's why this is the first line. A demultiplexer performs the opposite function to that of a multiplexer. Let me show you an example by taking a 4:1 multiplexer. As you have already know that in a multiplexer, this 4 represent the number of input and this 1 represent the number of output. So these inputs are controlled by selection lines. With the help of various input combination of these selection lines, any one of the input channel will be connected with the output. So the data which is coming out from a multiplexer is now going to be the input of a demultiplexer. So this is a 1:4 demultiplexer. As I have shown you that in a multiplexer, a dialer is required to connect this input with the output. So at a time, any one of the input will be connected with the output. In the same way, the input of this demultiplexer will now going to be connected with each of the output one by one through a dialer. By using the dialer, the input can be connected with output A or B or C or D. This dialer is also operated by two selection lines. For a 1:4 demultiplexer, it requires two selection lines. As we have already seen that there is a relation between the input channels and the selection lines in a multiplexer. In the similar way, the selection line and the output of a demultiplexer has some relation. So for a demultiplexer, it has one input and multiple output. The data at the input end are distributed among various output channels. That's why the circuit is also referred to as a data distributor. Now let me show you how the output lines and the selection lines are related. Suppose n is the number of output lines in a demultiplexer. And let us consider m is the number of selector lines. So the output and the selector lines are related as n equal to 2 to the power m. Now you can write the number of selector lines m equal to log n with a base 2. Let us take a small demultiplexer, that is 1:2 demultiplexer. Demultiplexer can also be written as DEMUX in short. In a 1:2 demultiplexer, the number of outputs, say n, equal to 2. Now put the value of n or substitute the value of n in the above formula, m equal to log n base 2. So you will get m equal to log 2 with a base 2, which is equal to 1. That is, one selector line is required to control 1:2 demultiplexer. So this is the block diagram of a 1:2 demultiplexer. It has a single input channel and a two output lines and a single selector lines. You can also attach an enable line. This enable lines, when high or logic 1, the circuit is operatable. That means the circuit is active. When the enable line is 0, the circuit will not work. And this is the truth table of 1:2 demultiplexer. When E is 0, whatever may be the values of selector line, you will get nothing in the output. So that's why I have written cross under S and output as X. That means whatever may be your S input, you will not get any output. Now when the enable line is high and the S selector line is 0, at that time the data at the input I will move to output A. That's why I have written A in the output column. And when S is 1 and the enable is also 1, at that time the data at the input I will now move to the output B. So that's why I have written B in the output column. Let me show you this truth table in more details. So this will be the actual truth table from where we are going to derive the Boolean expression. After that we will draw the logic diagram of 1:2 demultiplexer. Since there are two outputs A and B, so I have written two columns under the output A and B. When E is 0 and whatever the value of S, both A, B output will be 0. Look at the last two row. When E is 1, When E is 1 and S is 0, the data at the input I will now directs to the output A. That's why I have written I in the A column. At that time, B will remain in the 0 state. When S is 1, keeping the enable high, the data at the input I will now move to output B. That's why I have written I in the B column. So this will be your final truth table for the 1:2 DEMUX. Now let's write the Boolean expression from this truth table. So this will be your two Boolean expression because you have a 2 output in the 1:2 demultiplexer. We are not going to consider the first row because at that point of time the enable is low and X is in a don't care condition, and in this situation we are getting nothing in the output. We are going to consider the last 2 row. Look at the A column first. So in the A column we are getting input I over here. So at this time enable is high and S is 0. That's why I have written A equal to E is high, and since S is 0, so write S complement along with I. In the last row we are getting I input in the B column. So in this situation, look, E is 1 and S is 1. So just write simply E and S. Since they are occurring at the same line, so they are connected with an AND operation. Now by considering these two Boolean expression, let's draw the logic diagram. We require 2 AND gates because there are 2 expression and both the expression contains an AND gate. And so we require 2 AND gate with 3 inputs. So draw 2 AND gates which will give you the output A and B, and obviously it has a 3 input. Now look at the expression. The selector line is controlling the whole circuit, so draw the selection line first, since there are S bar in the first expression and S in the second expression. So we have to draw like this. So this is the S line and this will be the S complement line. To make it a complement, we have to attach an inverter over here. So this will be treated as S and this will be treated as S bar, or you can say the S complement line. Now look at the expression. Both E and I are common to both the expression. That's mean E and I lines are connected with both the AND gates. So you can draw like this. E and I has a connection to both the AND gates. So when E is 0, the output of AND gate will become 0. That is the first row. Data which are coming into the input will pass through A and B, but this input will be controlled by the S line. That is the selector line. So look at the first expression. Here it is written S complement. So you have to draw a connection from S complement and attach with the A AND gate. This is a connection from S complement and connect with the A AND gate. In the second expression there is simply a S. So draw a connection from S line and connects with the second AND gate and you will get B. So this is the complete logic diagram of 1:2 demultiplexer. If you understand the design procedure of 1:2 demultiplexer, I think you can now draw the higher order demultiplexer just like 1:4 or 1:8 demultiplexer. Let me show you some advantages of demultiplexer. For transmission of audio and video signal requires combination of multiplexer and demultiplexer. They are also used as decoder in security system. Combination of demultiplexer and multiplexer increases the efficiency of a communication system. Demultiplexer can be used as serial to parallel converter, because as you have seen that a demultiplexer has a single line, so whatever the data coming into the input line are coming serially, and it has a multiple output lines, so the data are distributed among various output lines, so you can say that data are moving through the output parallelly. It can also used in wavelength router. So now if you have any problem or have any further queries, please write down in the comment box. I will try to reply you back as soon as possible. So this is all for this video. Thank you. Subscribe to my channel Online Technical Mentor and press the bell icon for latest update. Thank you.